All right, section 3.2, we're going to talk about ionic compounds and binary ionic compounds. Okay, so I'll just kind of read this and kind of go through it as we're reading it. So atoms of elements that lose electrons easily are mostly metals. Okay, they're mostly metals, and they form positive charges known as cations. So cations, okay, have plus charges. These, most of the time, 99% of the time, are the metals. Now, you remember on the periodic table, things we had like that staircase, right? Things to the left of it were the metals. Things to the right of it are the nonmetals. And then things on the line were metalloids, okay? But all metals, not most metals, every single metal forms a cation. That means they lose electrons. We're going to talk about why this is in a second. All right, and those that gain electrons easily, those are the nonmetals, are called anions. All right, anions form negative charges. These are the nonmetals. All right, and this is always the case. Okay, easy to remember. Cation has a T in it. Notice that T looks like a plus symbol. So cations are plus. Anions has an extra N for negative. Very simple. All right. One of the things that you have to be able to do is to be able to recognize if something's ionic, meaning it has a plus charge or a negative charge. Okay. So it's important to recognize that in the context of chemical interactions, these two things do not happen independently. Okay. Meaning you don't just form a cation. All right. If you form a cation, you also have to be forming an anion at the same time. So if I have a metal and I'm reacting it with a nonmetal, right? An electron from the nonmetal has, an electron from the metal has to go, the electron from the metal has to go to the nonmetal. So if something loses, something also has to gain at the same time. These both have to occur at the same time. You cannot have one without the other. So an electron lost by an atom, all right, is always gained by another, and you have this electrostatic interaction between the opposite charges, and we call that an ionic compound. All right, so sodium is a metal, it likes to lose an electron, and chlorine likes to gain an electron. So you have these opposite charges attract towards each other, all right, and you have sodium chloride. Okay? So these binary compounds, so basically I just kind of did this exact page for you. So the positively charged sodium ion and negatively charged chlorine ion are attracted towards each other, and they are drawn together to form an electrically neutral compound. This is the important part, neutral compound, meaning overall zero charge, which we represent by the chemical formula NaCl, okay, which you would write it as this, NaCl. This is kind of a little bit inaccurate. You do not have the charges still. This is how you write the formula. The electrostatic interaction between the opposite charge ions are what we call an ionic bond. So this attraction right here is an ionic bond. All right. They form mostly between metals and nonmetals. Okay, we've already talked about that. And it has to be neutral. So sodium has a +1. Let's say I take sodium, which has a +1 charge, and oxygen, which usually has a 2- charges. On the next page, I'm going to talk about how you know what these charges are. Okay. Now, in order to write a balanced formula, you have to have an overall charge of 0. So how many of each of these do you need to have an overall 0? Well, this oxygen has a 2- charge. Sodium has a +1 charge. Well, if I had 2 sodiums, this overall would equal 2+. Plus 1 oxygen is a 2-. These together equal an overall charge of 0. So this is how you know what the formula is for sodium oxide, Na2O. And it's as simple as that, as how you know what the formula is. Okay? We're going to talk about some other tricks. I call it the crisscross applesauce, that the charge here goes down there, the charge here goes down there. In most cases it works, but other cases it doesn't. We'll have to talk about it. So let's talk about how we find these charges. All right? So I kind of have a blank page here. All right, last chapter we talked about filled orbitals, or shells, completely filled shells, and we talked about isoelectronic. Okay, this is, guys, I'm going to give you the secret of life right now. Get your pens ready. All right, I'm giving it to you. Every atom Okay, everything wants to be isoelectronic. That means that isoelectronic, so let's put down here, isoelectronic with its closest noble gas. Okay, remember, isoelectronic means the same configuration, different atom, same electron configuration, different atom, same electron configuration. Okay, so let me draw a periodic table here. Okay, that's why they're called noble gases. Everything wants to be noble, like its closest noble gas. Okay, so here are the noble gases. We have helium at the top, neon, argon, krypton, xenon, and we don't talk about radon. All right, so put hydrogen, lithium. That's it. 1, 2, 3, 4, 5, 6. There we go. Boron, carbon, nitrogen, oxygen, fluorine. Okay. Let's kind of write that a little better. Lithium, beryllium. Okay. Let's talk about fluorine. Okay, fluorine, electron configuration. I'm going to write out the orbital diagram. 1s2, 2s2, 2p. So 1s2 are filled. 2s2, 2p5. 1, 2, 3, 4, 5. Okay, everything wants to be isoelectronic because it wants to have its outermost shell completely filled with electrons. So what does fluorine have to do to be completely filled with electrons? It needs to add one more electron into its outermost shell to be completely filled, to have all of the 2s completely filled. Okay, so that means fluorine has to have the same electron configuration as neon. All right, so if fluorine gained one more electron, it would have the same electron configuration. This is the electron configuration for neon. Okay, it's also the electron configuration for F minus. Okay, it's also the electron configuration for oxygen 2 minus. If oxygen gained 2 electrons, 1, 2, it would have the same electron configuration. This is what it would be. Same exact thing, 1s2, 2s2, 2p6. Okay, nitrogen 3 minus. It gained 3 electrons. All right, it has 3 and it's 2p, 2p3. If it gains 3 more electrons, it now is 2p6, just like neon, okay? Now, you always want to go to the closest noble gas. So for example, lithium. What's closer to lithium, helium or neon? Obviously helium is. So lithium needs to lose 1 electron to be like lithium. So to be like helium. So lithium loses 1 electron. Lithium is a 1s2, 2s1. All right, so if it lost 1 electron, all the 2s are gone, and now it has the same electron configuration, 1s2, as helium. So lithium gains a +1. So it's isoelectronic with helium. Beryllium, same thing, it's going to lose 2. 1, 2. It could gain 6, 1, 2, 3, 4, 5, 6, or it could lose 2. It's easier to lose 2. So beryllium becomes a +2. All right, sodium is right here, and Ernie, sodium, give me a second, I believe magnesium, that's correct, magnesium. Sodium could be like argon, or it could be like neon. It's in between neon and argon. Well, if it loses 1 electron, it's like neon. If it gains 7, it's going to be like argon. Well, losing 1 sounds a lot easier. So sodium is going to have the same electron configuration as neon, which remember is this right here. So sodium plus is also isoelectronic with neon. Magnesium is a 2+. Aluminum is right here. Aluminum is a 3+. Guess what, guys? All 6 of these ions have the same exact electron configuration as neon. That's the meaning of life, guys. That's what atoms want to do. That's what they strive to do. They strive to be exactly like its closest noble gas. Okay, now we're just talking about the main group elements, group 1A, 2A, 3A, 4, 5, 6, 7, 8As. Okay. Group 4, we're going to kind of ignore, at least carbon and silicon, because they can gain 4 or lose 4. There's a whole class all about carbon. You'll learn about it if you take organic chemistry. Organic chemistry is all about the chemistry of carbon. So because it can do both, we kind of save that for a different class. So don't really worry about those two. Okay, so lithium is a 1 plus. Sodium is a 1 plus. What about potassium? What do you think potassium wants to do? What's closer, argon or krypton? Argon, it's going to lose 1. Right. So everything, I'm assuming you're right. That's why I said right. Everything in the 1A all have +1 charges. Everything in the 2A, so calcium, strontium, barium, magnesium, beryllium, they all have a +2. Boron, aluminum, I believe isn't tin in this category? No, indium, gallium, thallium, they all have +3 charges. 4 we're not going to worry about. Now, nitrogen, underneath nitrogen is phosphorus. Okay, I believe 10 is also in this row. No, I'm sorry, ignore 10. I keep talking about 10, forget 10. Arsenic is in here. I'm sorry, arsenic or astatine? Yeah, arsenic, sorry. Arsenic is in here. These all have +3s. They're all isoelectronic with either neon, with the noble gas after it. These want to gain electrons. Oxygen, sulfur, all right. These selenium, these all have +5s. I'm sorry, -2s, -2s. Okay, -3s. Everything here, fluorine, chlorine, bromine, iodine, they all have -1s. Okay, so you have a way now to predict the charges for the main group elements. The transition metals aren't as straightforward. Okay, these I have to tell you because there's more than one charge in most cases. So if I were to pair up a magnesium, let's say, with a, let's say a iodine, okay, here's my cation because it's the metal. So what charge does magnesium always have? Well, here's magnesium, so it's a 2 plus, and here's iodine, non-metal, so that always has a 1 minus. So the formula is going to be MgI2. So you can figure out formulas now. I can give you 2 different elements and you can come up with the formula. Okay, remember how I get this is these have to balance each other out. Okay, for how I need 2 I minuses to cancel out that. All right, how about if we take, let's say we take beryllium and you add it to sulfur. Come up with the formula for beryllium and sulfur. All right, put it on pause and come up with it. Okay, I'm going to go over the answer now, so hopefully you put it on pause. So beryllium is also a +2. Here's beryllium. Okay, sulfur is in a 6A row, so it has a -2 charge. So how many of each do I need? Well, it's a 1-to-1 ratio. +2 -2 cancels each other out, so I need 1 of each, beryllium and sulfur. It's called beryllium sulfide. Now, there's a trick called the crisscross applesauce method. Okay, and the way it works is basically whatever charge you have here goes down here, and whatever number you have here goes down there. That's why I get MgI. Now in this case, if you did that, you would have 2 and 2. You'd have Be2 and S2. Well, that's not correct because you always still want the lowest common multiple between the two. So since I can divide them both by 2, all right, the actual answer is BES, since I can divide them all by 2. Okay, let me erase this so that we have some more space for additional problems. This is going a little slower than I thought. Okay, let's do some more problems. Let's now take aluminum, okay, and combine it with selenium. Yeah, selenium. Now here's the other thing it's important to remember. Sorry guys, I don't want this video. Well, just keep that there. Aluminum and selenium. There we go. All right. So what's the formula with aluminum and selenium? Well, aluminum has a 3 plus, selenium has a 2 minus. All right. So if you want the lowest common multiple, you have to figure out what the lowest common multiple is, which in this case it's 6. So this has to be multiplied by the number 2. This has to be multiplied by the number 3. So you have 2 aluminums to 3 seleniums. So this is a perfect example where the crisscross applesauce works, where you don't even have to do math. Okay, so if you just kind of erase these numbers, all right, just do the crisscross applesauce. The 3 goes down here and the 2 goes down there. And you get Al2Se3. That's it, guys. That is how you write formulas for the main group elements. These are called the type 1, which we'll get to in a later section, type 1 binary. Okay, and we'll learn how to name them in a little bit. Okay, but it's all based on this fact. Everything wants to be isoelectronic with its closest noble gas. Okay? Okay, so I might have went ahead of what these slides are, so let's just kind of read these slides. So a chemical formula identifies the ratio of the combined atoms. So like I talked about, you always want the lowest common multiple. All right, so sodium chloride, for example, is a 1-to-1 ratio. They have to equal each other in magnitude. So at the end, you have a 0 charge. All right, you have to combine them in a way so that it's equal. So everything is electronically neutral. We already talked about that. So if we take a calcium and add it to a nitrogen, all right, calcium has a 2+ charge, nitrogen has a 3- charge. So we have Ca3N2. That will cancel everything out. If you multiply this by 3 and this by 2, you'll get a +6 here and a -6 here for overall neutral charge. Okay. Here, this is kind of the crisscross applesauce method. They're kind of showing it to you. So lithium and sulfur, you see how the 2 goes down to there. The 2 there goes on the other side. The 3 goes there. The 2 goes there. Okay, so this is kind of the crisscross applesauce method that I already talked about. Okay, it's just showing it to you again. So here's some problems. Let's do some problems. Write the formula for the ionic compound that forms the following pairs. Now here's something important to note. Your cation is always written before your anion. Okay, so for example, lithium is the metal, magnesium is the metal, magnesium is the metal compared to chlorine, fluorine, and oxygen. So lithium, all right, lithium has a +1 and chlorine has a -1. So it's a 1-to-1 ratio, LiCl. That would be your formula. You do not write it as ClLi. The reason is because this is my anion and this is my cation. We always write the cation first, then the anion. So this is not correct. You would never write it the other way. You always write the cation first, which is usually the metal, then you write the non-metal afterwards. So just keep that in mind. Do the remaining 2, figure out what the formulas are, and I'll go over the answers. So put it on pause now. Okay, we should be back. And you should have magnesium has a 2+ charge because it's in the 2A row. Fluorine has a -1 charge, so your formula is Mg. I need 2 fluorines for every magnesium. And then for magnesium oxide, magnesium is a 2+, oxygen is a 2-. It's a 1-to-1 ratio, so MgO would be the formula. All right? Practice this. It's not hard. There's lots of problems in the book. We will do problems in class, but make sure that you are able to do this, do the main group elements, and we will continue on in the next video with naming and a little bit more complicated examples.